Hi guys, welcome back to my channel. So today we'll be explaining or solving an example under Euler's Lagrange equation, which is under calculus of variation. And I've solved few examples under calculus of variation. It's under example. So find the extremals and the stationary function of the functional. I've explained what functional means, so if you probably have issues with this, then you might probably have to watch the videos I've uploaded before. Kindly subscribe to get notified when I upload more videos. So solution to this, they gave us a boundary of y of 1 equals 0 and y of exponential equals 1. So this is the main question now. We have to find the extremals and then the stationary function of the functional. So if I want to do this, the first thing I'm going to do is to compare with the functional this, and then this functional, if I compare this with this, I notice that I have my f of x comma y prime equals x y prime squared plus y prime. Now if that is the case, I'm going to use the first form of Euler's Lagrange equation to solve this. You can either choose to use the first, second, or the third form. I've explained and I've proved for all forms. You can watch the previous videos to get the formula. So I'm using the first form of the Euler Lagrange equation, which is di f di y minus ddx of di f di y prime equals 0. That means I have to look for di f di y. I'll also have to look for di f di y prime for me to go further with this. So that means this is my f. Now I'm differentiating this partially with respect to y. If I differentiate this partially with respect to y, look at it, di f di y, right? I'll look for where I have now this, any other thing that is not y here will be taken as a constant. So that means here x and y prime is a constant. So if I differentiate this, I'll have 0 plus. I differentiate y and y prime, I'll be using product rule. I've explained the cheats to product rule, or like a trick to product rule, one of the videos I uploaded, so you can just watch the videos I uploaded one time before for you to get the full explanation to this. Although I'll still explain this now, you can just follow me. So this is to differentiate this, you have y and y prime. That's product rule, right? So I want to differentiate partially with respect to y. That means any other thing will be taken as a constant. So what I'll do is I'll differentiate one, leave one, then leave one, differentiate one, or you do the trick I explained the other day, which is if you have y prime, so I bring this down, differentiate this, I have 0 because differentiate y, I have 1 because I'm differentiating partially with respect to y. If I differentiate y prime, I have 0 because I am differentiating partially with respect to y, which means any other thing that is not y here will be taken as a constant, and if I differentiate a constant, I will have 0. So then I cross multiply, so that means I'll be left with y prime. That is why if I differentiate di f di y, that means differentiate f with respect to y, I'll have y prime alone, which is what we have here. Now differentiating f partially with respect to y prime, I'll have, so for me to have di f di y prime, right, it means any other thing that is not y prime here will be taken as a constant. So I'll have this to be, this is x and this is y prime. So I do this separately. I just want to explain this well so you guys will understand. So I bring this down, this will be 0 because it is a constant. Then if I differentiate y prime squared, I'll have 2y prime, so cross multiply. So the first part will be 2y prime x. Now differentiating the second part, I'll have y prime with respect to y prime, so this will be 0, this will be 1, so cross multiply, you'll be left with y. That means if you differentiate this, you should have 2y prime x plus y. I hope you understand. Now putting all these into equation 2, I will have y prime plus di f di y is y prime minus ddx of 2y prime x plus y equals 0. Now I differentiate the bracket, and from to differentiate the bracket, it's the same thing here. I'll do product rule also. Now the bracket here, what I have inside the bracket is I have 2y prime x, right, plus y. Now I'll differentiate this first. So 2y prime x. Differentiate this, I'll have 2y prime prime. Differentiate this, I have 1. So if you cross multiply, you have 2y prime plus 2y prime prime x. If I differentiate y, I'll have y prime. So that's why I have plus y prime here. So I have 2y prime plus 2xy prime plus y prime equals 0. Then I add. So if I add, I have 2xy prime. 2y prime plus y prime will give me 3y prime. So that's why I have 3y prime here. Then I open the brackets with the negative sign I have here. So I have y prime minus 2xy prime prime minus 3y prime equals 0. Now y prime minus 3y prime implies I have minus 2y prime. So minus 2y prime equals 0. So now here I factorize minus 2 out. I have xy prime prime plus y prime equals 0. Divide both sides by minus 2. I'm left with xy prime prime plus y equals 0. Now we have the differential equation, second order differential equation, but what we really want to do is to reduce it, get our y, and put in our boundary that's been given to us, and look for the stationary function. So that means I'll have to integrate, right? So for me to integrate, I'll let u equals y prime. That means u equals dy dx, u equals this y prime. Then if u equals y prime, if u equals y prime, then u, if I differentiate, okay, then I let u prime equals y prime prime. That means if I differentiate u prime, I'll have y prime prime, right? So now I'll put this into the equation. So I have x y prime prime plus y prime equals 0 will become x. Anywhere I see y prime prime, I have u prime. So I have x u prime plus y prime is equal to what? U. So u equals 0. Then x u prime equals, I'm taking my plus u to the other side. So I have x u prime equals minus u. And I said u prime is the same thing as the u dx, right? If I have y prime, it's the same thing as the y dx. So u prime equals du dx. So here, if I'm telling you that my u prime equals the u dx, then I can separate using I separate x away from u, and then I integrate. There's this method we call it. So here I'll have x du equals minus u dx, and I bring x to the other side, u to the other side. So here what I'm going to do is just x du equals minus u dx, divide both sides by by u. I have du over u. Divide the other side by x. I have minus 1 over x dx. Now if I have that, then I can easily integrate both sides. Now if I integrate both sides, I'll have ln u equals minus ln x plus c. After integrating, you must always add your constants. So that's why I have ln u equals minus ln x plus c, because if you integrate 1 over x equals ln x, if I integrate 1 over y equals ln y. So I take exponential of both sides. I have e raised to power ln of u equals ln of x raised to power minus 1. Using your law of logarithm, this will come to the other side. So we have x raised to power minus 1 plus e raised to power c. Then I take this to the other side. I have e ln u minus e ln x raised to power minus 1. That's exponential of. So using law of indices again, I can say this is equal to this using law of indices. So I have e raised to power ln of u over x raised to power minus 1 equals to e raised to power c. Then ln will cancel your e. Then I have u over x raised to power minus 1 equals e raised to power c. But I don't want to write e raised to power c, so I'll say c1. Then I'll tell you that where c1 equals e raised to power c. So my u over x raised to power minus 1 equals c1 from here. And I can cross multiply. If I cross multiply, I notice that I'll have u equals c1 x to the power minus 1. Now remember, or you recall that I said here I said u equals y prime. So if u equals y prime, that means u equals dy dx. So I come back here, anywhere I have u, I put dy dx. So that's why I have dy dx equals c1 x to the power minus 1. Now if I want to integrate, like I said, we're looking for y. That means I have to keep on reducing y and y prime prime, or y prime and y prime prime, so that I will have just y, and then impute my boundaries and get my stationary function. So now I still have y prime, so I still need to integrate to reduce to get my y. So here I will separate. So I have dy equals c1 x power minus 1 dx. So for you to integrate, then you integrate both sides, then you have y equals, because if I integrate dy I have y. I've explained this before in my previous videos. So I have y equals c1 ln x. After integration, I told you that you always have to put your constant, so that's why I have c2. I don't want to put c again because I want to differentiate my constants, as I have c1 and c2. Now I already have y equals c1 ln x plus c2. This is my particular solution. Yeah. Yes. So I'll have to impute my boundaries into the equation for me to get c1 and c2, and then get my general equation, like my required stationary function. So now from the question, it said y of 1 equals 0. I've explained this before, and I'll explain again. When you have y of 1 equals 0, you call that in mathematics, when you have y of x is equal to y, that means anytime I have y of 1 equals 0, automatically my x equals 1 and my y equals 0. So for the second one, you have y of e equals 1. It implies that my y equals 1 and my x equals e. So for the first condition, we have y of 1 equals 0. So that means x equals 1 and y equals 0. So if x equals 1, y equals 0, I put it into this equation asterisk. So I'll have 0 equals c1 ln 1 plus c2. Then ln 1 equals 0. So 0 times c1 will be 0. I'll be left with c2. Then it implies that my c2 equals 0. Equation A. Then for the second condition, y of e equals 1 implies x equals e and y equals 1. So y equals c1 ln e plus c2. Then 1 equals c1 multiplied, so ln multiplied by e is going to give you 1 automatically. So that's 1 equals c1. So that implies that your c1 equals 1. Sorry, not 1 equals c1. So your c1 equals 1. So you've gotten answers for c1 and c2, and I put them back into my equation asterisk, which is this. So if I put c1 and c2 here, I'll have y equals c1 is what? 1. So I have 1 ln x plus 0, which is y equals ln x. And ln x is your required stationary function, which is a solution to the problem that has been given to you. I hope you understand. If you really do understand, you can like my video and then subscribe. Thank you very much for watching.